Okay. So again, we have our friend. The model of a function of x, y, z on a small x, delta x, delta y. Slope in this direction is a partial derivative with respect to y. Slope in this direction is partial with respect to x. What if we want the slope in some other direction, like this direction? Okay, so that we have an x component and a y component down here on the xy plane. How are we going to get that slope? Well, I just said we're going to do some combination of this slope and this slope. If we go slowly from here to here, the slope changes continuously. Okay, so at every intermediate point, there's some combination of this slope and this slope. Turns out just a simple linear combination with a sine and a cosine. And we're going to see how that works. So first, let's just think, okay, we've got the xy plane. We want to find the derivative, find the rate of change. Find the rate of change here. In the direction of a unit vector u. Let's just say u. Is this correct? We're going to let u equal cosine theta I plus sine theta j. We know that a unit vector in the xy plane can be expressed as cosine theta I plus sine theta j. And of course, theta is the same. So it's kind of like a unit vector in direction theta. Theta is the angle that we're going to travel in relative to the positive x direction. Well, to be specific then, we're going to find the rate of change of some function f of xy, which is implicit, it's understood, and better write it out. Okay, we might just track it again. Okay, well. We find the average rate of change over a displacement delta x equal hu, where h is going to be something that we allow to approach zero to get the instantaneous rate of change. So we're just mimicking what we do with the definition of any rate. Let's say this point is x naught, y naught. Okay. It's H cosine theta times I plus H sine theta times J. So what we would be looking at is the point X naught Y naught. And I'll draw that down here. And here's X naught. Y naught. Here's some multiple of U. What are the coordinates of this point? Tell me what the coordinates of this point would be. If we displace ourselves H times U, where U is cosine theta I plus sine theta J, so that HU is this. What are the coordinates of this point? Can you write the coordinates of that point? We start at X naught, Y naught and travel along HU. Well. Probably should have written those parentheses for one of them. Maybe some kind of a prompt. Well, HU is this. So what we're going to get should be pretty clear. We go X naught plus H cosine theta for the X coordinate, right? And Y naught plus H sine theta. Okay. So that the average rate is, well, the change in is F of X naught plus H cosine theta, Y naught plus H sine theta, minus F of X naught, Y naught. So again, with our block, everybody's got a block they can look at. Look at your block and see what you think. Okay, if we go in this direction here, okay. Well, the X direction's out here. And Y direction's here, right? Actually, I kind of reversed my direction. Look, we would be going in this direction. Okay. So I'm going to change my picture. Let's say this is our point X naught, Y naught down here in the XY plane. And this is our point on the graph, which is X naught, Y naught, F of X naught, Y naught, those are the coordinates, okay? So if we go at an angle like the one I depicted there, of course, the X-axis is this way, the Y-axis is this way, we'd be going like this. Okay. We start at the X naught, Y naught point. We move toward X naught plus H cosine theta, Y naught plus H sine theta. And what happens? Well, we go higher or we go lower. So it's pretty level there, but okay, depending on the function. And F X naught, Y naught. Sorry, F X naught plus H cosine theta, Y naught plus H sine theta is how thick this thing is at this point. Okay. Hopefully that clarifies things a little bit, at least get you thinking in 3 dimensions. So the change now is just the value of F at this point minus the value of F at this point. You can visualize that too. Okay, so the average rate of change is this expression, just a change in F, divided by the distance, okay? Divided by how far we go, which is just H. So we go this far, we get this much change. The average rate of change is how much F changed, how far we divided by how far we went. That makes sense? So there's our basic idea of the average rate of change, and then the instantaneous rate of change is just the limit of this as H approaches zero. It turns out, I'm not going to write out the details of it. Although I'd like to, and maybe I will later, depending how much time we have and how much time we need. Turns out that the limit as H approaches zero of difference quotient. Is just this combination of partial derivatives times cosine times a sine theta. Fairly intuitive, but you can work out the details. You can read those details in your text. The algebra of simplifying this and something that's pretty straightforward. In any case, this is the definition of a derivative, and this is the way it works out. Okay. What this means, take the partial f with respect to x, evaluated at x naught y naught. Partial derivative with respect to y, evaluated at x naught y naught. Okay, I can write this in slightly different form. I define this thing, call this a del. It's not a delta, it's upside down. It's got an arrow over the top of it. And delta is just a symbol for change in it. So this is different, okay? Different symbol, it's called the del symbol. If del F is this, it's just a combination of x and y derivatives. But x derivative in the x direction, the I direction, y derivative in the j direction. And what we did up here is it's equal to del F dot U. So write that out for me and show me that del F dot U equals just what we have up here. Okay, so it's very easy to write that out. Okay, so Okay, so, well, I dot I is one, right? She's been distributed along. Do this, times this, and we're gonna get partial F with respect to X times the cosine of theta. And then I dot J is 0. So we're not gonna do this in a minute. Okay. J dot I is 0, so that's this part's gonna give you 0. And J dot J is 1, so we're gonna have partial F with respect to Y times the sine theta. Thing else is identical to this, except of course I didn't put my X naught Y naught in there, but that's just there for clarification. So at any point, not just X naught Y naught, this is the directional derivative. Okay. And you know, hey, I didn't actually look at the text, and I should have. But I think they use capital D for the subscript U vector, the derivative in U direction. Okay. I'm even going to. That's a derivative. Okay. If you can do derivatives, it's really easy to calculate once you got a function with some bizarre combination of composites and quotients and stuff. And, you know, then it's not hard. It's just a lot of bookkeeping. And it's error prone if you got a whole lot of stuff in your derivatives. But the idea, we know how to take derivatives. And do we always execute it correctly? Hopefully, yes. Okay. And the derivatives you're asked to do for the homework aren't terribly complicated. Okay. Doesn't mean they don't get that way. And if they get complicated enough, you really have to know the rules. But then you're really going to go to the computer algebra system. Okay. Take the derivative of arcsecant of some rational function with big polynomials in the numerator and denominator. Maybe some square roots and then a big old denominator on top of that. It's almost pointless after you've learned to take derivatives, learn the basics, to actually go through the pages of calculation you would need to get that derivative. That's where computer systems can be useful. Just like long division. If you do a long division of a 10-digit number into a 12-digit number, you're going to be at it for a while. Well, we use a calculator for that. You should be able to do it. But you shouldn't go to the trouble once you know how to do it. Okay. Kind of an art to know when to go to the crutch of technology. And so that it's not a crutch. So it's just enhancements at time saving. Different between the time saving and a crutch can be real subtle. You've got to be careful about that, especially with AI starting to take off. And that's only just begun. Okay. Well, that's the directional derivative. The other thing you should know about it is del F is your gradient. And you see, if you got any reasonable function, it's really easy to calculate the gradient. And what's the significance of the gradient? Say it this way, using the direction of the gradient, the rate of change is maximized. Okay. Which means that the gradient gives you the direction in which the function increases most rapidly. Now, in physics, just quick mention of that, for those who are in physics, and also for the benefit of those who still have to take physics. Okay. The easiest example to understand is heat flow. Okay, heat flows from high temperature to low temperature. Now, if you got a big old chunk of rock that's been heated differently at different points, you know, it's sitting on top of a campfire, the sun's acting on this side, and there's an iceberg up against it over here. And probably not an iceberg, because then you'd be in the water and it'd be hard to have a fire. So it's a glacier. So it's resting against a glacier, sun's on it, and there's a fire under it or right next to it. Okay. So the temperature distribution inside that rock is pretty complicated. But there is a function that describes it at any instant. Okay. And at any point in that rock, heat is flowing in the direction from hot toward cold. Okay. Well, that's the direction of the gradient, whatever the gradient might be at that point. All right. And gradient is also exactly what we use to find electric field from electric potential function. Electric field is a gradient of the potential function. Well, that's easy to solve. It's a little complicated to derive. Although in most cases it is. And we'll talk about that in physics. But there's your gradient. Gives you the direction in which something increases most rapidly and the rate at which it increases. Okay, well, that's pretty much it for the rest of the course. So let's just do an exercise. Well, you can answer those. There are a couple of potential pitfalls in that question. Let's see if you can navigate the pitfalls. They're not difficult pitfalls, and I'll help you along with them if necessary. But can we use this definition for the directional derivative? Well, actually, it's limit definition, but the results that come about directly from the limit definition. Okay. In other words, this basically, and this definition of directional derivative. Okay. Can you use that definition to answer the question? Okay, somehow I think I did the code for that. Here we go. I was trying to find this directional derivative. I'll give you the hint. U is 2i plus 3j. The unit vector in that direction. With that hint, everybody got it. Some people had it even without the hint. Some people were using this as always a unit vector, which it clearly is. Right? And they're saying the cosine theta equals 2, sine theta equals 3. Cosine theta and sine theta can't exceed 1. Okay, so there's a red flag that you're going to kind of pick up on. In that case, as soon as we got straight that you had to make this into a unit vector, everybody did it correctly and did the rest of the calculation, right, as far as I can see. So that's good. Just be careful about that unit vector. So here are the details. U is equal to this vector divided by its magnitude, which gives you this 2r squared 13i, 2 to the square of 13j. So the del F is just the x derivative of this 3 times I think that's right. And the y derivative is this times j. And then we just do the dot product of del F with u. And then I just wrote it out because everybody, I think, did it correctly. But I just factored out the 1 over square root of 13. And then did the rest proportion. So what you get? If I did it right and you did it right, you should agree. Then the question is, what direction does F change most rapidly and at what rate? See if we can answer that in terms of what I've told you so far. Again, that requires some interpretation. And I'll help out if you need it. Okay, so as anticipated, some people have moved from this. Remember, before I take this away, if U happens to be in the direction of the gradient, the rate of change is maximized. Okay. So to answer the first part of the question I asked, what direction is the rate of change maximized? Well, the directional derivative is your rate of change. If you want to maximize it, you're going to have to take the gradient and express its direction. Okay. Now that's going to get a little complicated out right. But not completely out of hand. Okay, so I use ROC for rate of change. Maximum rate of change is in the direction of the gradient. And the gradient is you're writing it here. I'm going to read it to you. You got it anyway. Okay, so you know what the gradient is. So what's the direction of the gradient? Well, you can define the direction of the gradient by the direction of a unit vector in the same direction. Okay. the directions out of the unit vector. Del F over magnitude of del F, right? So, what's del F over magnitude of del F? Just write down the expression. It's somewhat long. It's complicated, but you can write it down. Okay, so. Very simple. Del F goes to the numerator. And in the denominator, you have the square root of this square plus this square, which could be expanded and simplified. Okay. And if you're going to do a whole lot with it, you want to do that. But right now, until we really need to expand it or anything. I think everybody got that real quick. So you wanted to punish yourselves and started expanding and simplifying it. And it's really good exercise to do that. But other than clerical errors, I don't see anybody would have any trouble doing that. So, well, okay, so that's fine. So what's theta? How are you going to find theta? Okay, so what's theta? Well, among other things, this is a unit vectors that has a form cosine theta I plus sine theta j. So cosine of theta would be just the x component or the I component. The sine of theta would be the j component. Okay. Want to write out that whole denominator again, same thing it was here. Of course, that's a complex fraction, so you might want to simplify it a bit, but you kind of cut to the chase. If you use the tangent of theta, the tangent of theta is sine theta over cosine theta, and that denominator just cancels out. Okay. So you'd have this over the denominator, this over the square root, divided by this over the square root. You do the reciprocal multiply, you just get this over this. So it's just going to be this over this. I would multiply both the numerator and the denominator by the square root of y to get rid of that fraction in the numerator. Just to, if I was going to use the expression, it just so easy to do that. And of course, now we use the inverse tangent of that. However, the problem is the inverse tangent just gives us an angle between 0 or between -π/2 and π/2. It doesn't give us anything in this second or third quadrant. Well, what we have to check then is whether the denominator is positive or negative. Okay. We've got to add pi 180 degrees, and what unit you're using for your angle. And sometimes you will use, when you calculus with it, and you go to degrees. We'll leave it as right. Although you go to degrees, so, and of course, what's in the parentheses is just this guy. Probably simplified form. I can write it. I write it as x squared square root of y minus x over 2x minus 3/2 minus y. Maybe I put that way. Okay. And that's not really what's important. What's important is to see that now you know the direction of maximum increase or decrease at any point. You know the gradient at any point. And you also know well, what is the rate? I wrote it down, so let's. It's a derivative, it's a directional derivative in the direction of the gradient. Well, the directional derivative in the direction of the gradient is gradient of f of x, y, dotted with this mess, right? The direction of the gradient is this. Okay. I don't have room to write it out. Show me for this gradient then what del f of x y dot del f of x y is. In other words, go ahead and write this out. Matter of fact, write out the whole thing. You've got the expression for del f right here. Right? So just write del f, replace del f with this, with the magnitude of del f in the bottom and the top. So you show me what it is. And I think you're going to like it. Okay. So we're trying to simplify this and everybody's written out a lot of stuff. Okay, sometimes in a form that's really accessible to what needs to be done, sometimes not, okay? And you don't know what form it's gonna be, and it's always been a good form. Just isn't always the simplest form, the form that makes the simplification most obvious. What makes it obvious is the fact that you have to know that V dot B is the magnitude of V squared. Okay, if V is AI plus BJ, what's V dot B? It's A squared plus B squared. What's the magnitude of V? A squared plus B squared. Okay, that's true for any vector. So what we get here magnitude of the gradient squared over the magnitude of the gradient. Which simplifies just to the magnitude of the gradient, okay? So the gradient has a magnitude and a direction. Direction tells you where you go, what direction you go to get the maximum increase. Now, if you got heat flow, I think I might have misstated before, because if you got heat flow, that tells you what direction the heat flows, but it flows opposite to the direction of the maximum increase, which is direction of maximum decrease. So it's from hot to cold, which is opposite to the direction of the gradient. This was an example. I think you got a temperature example in your homework. Okay, so the arctangent of y component over the x component, if you wish, the z component over y component of your gradient gives you the direction. You got to check to make sure you're in the right quadrant. Okay. And then magnitude of the gradient tells you what the maximum rate of increase is. Okay. And the maximum rate of decrease is the opposite. So that's a big deal. Another thing about gradient, I gave you a function of x, y, and z. Well, let me just. Yeah, I don't know if I told you. Do that other thing. Give your board a little bit of space on it. Okay, here we go. The gradient f of x, y, z x, y, f of x, y, z equals x, y, I plus y, z, j plus x, z, k. You write down the gradient of that function. What I asked you to do actually is impossible. I wrote it down without thinking. Okay. The gradient only applies to a scalar function. It doesn't apply to a vector function. Okay, but there's an important application where we do del dot f of x, y, z. Okay, so let's do that. Some of you actually did that. We do a dot product with this. Well, I dot I is one, so we would do. Partial with respect to x of x, y. Plus partial with respect to y of y, z. Plus partial with respect to z of x, z. Which is just y plus z plus x, or x plus y plus z. That's what you would do if I didn't put a dot there. What you would actually do if I hadn't put a dot there is you say, yeah, you just asked me to do something that can't be done. Okay. You have to have a function of x, y, and z. This is an important thing. It's called the divergence. Might as well know it now. Calculate it, because calculating it is easy. You can do the derivatives. You can. Okay. Interpreting it. Well, physics students, that's how you prove Gauss's law. Okay. So we get to that near the end of the course. Still, it's an important definition. And should have given you just a function, 3 variables rather than an effective function. And also I'd have to call this a different function. All right. So the other thing I was going to illustrate with that is pretty obvious. I don't think you'll have any trouble with it.